Okay, we did this we talked about differentials. So let's recall what that is again. If I have a variable u which is equal to the function, let's say cosine x, then what's the differential u? The differential of u is the derivative of cosine, which is negative sine x multiplied with the differential of x. And if I have u get to be given by the function, let's say 4 times tangent of x, then the differential of u would be given by 4 times secant squared of x dx. Okay, so what is our goal? Well, our goal is sort of our goal is to come up with a rule that's going to help us find antiderivatives of some more complicated functions. Okay, and what we want to do is we want to use the chain rule in reverse. Okay, so let's recall the chain rule. Suppose that I have the function x cubed plus 1 and to the power, say, 3, and if I take the derivative of that, what is the derivative? Well, the function that I have here, that function is the composition of what functions? It's the composition of x cubed and x cubed plus 1, right? So x cubed plus 1 is the inside of the composition. X cubed is the outside of the composition. You agree with that? So then, by chain rule, what's the derivative? By chain rule, the derivative is you take the derivative of the outside, which is 3 times x squared, right? But instead of x, you evaluate the derivative of the outside at the inside, right? You evaluate the derivative of the outside at the inside, so you put x cubed plus 1, and then you multiply by the derivative of the inside, right? Isn't that what chain rule says? Yeah. Is everybody okay with that? Yeah. So then, if I want to use the chain rule in reverse, what does that mean? It would mean that I have to start with something like which is equal to what? This is equal to 9x squared multiplied with x cubed plus 1 to the 2. So I have to start with an integrand where I have 9x squared times x cubed plus 1 squared dx, and I have to come to this x cubed plus 1 to the 3, right, with the plus c, or I'm going to ignore c for a second. So if I want to find the antiderivative of 9x squared times x cubed plus 1 squared, then that would be x cubed plus 1 cubed. But if I give you a random integrand like this, it's not easy to see that it is the derivative of x cubed plus 1 or something else. You agree with that? If I didn't show you this, right? If I just asked you this, right, would you be able to say this right away? No. So using the chain rule in reverse is actually harder. Okay, and first of all, let's look at the fact that how does the integrand look like here? The integrand, notice that it has two factors, right? The integrand here has two factors. One factor here and the other factor here, okay? And notice that one of the factors is a composition, right? It is the composition of x cubed plus 1 and x squared, right? And the other part, the other factor is almost the derivative of the inside, right? The x squared, I mean, if I had 3x squared, that would have been the derivative of the inside, right? You agree with that? So usually, whenever you have an integrand where you have two factors, one factor is a composition, and the other factor is the derivative of the inside of that composition, then you know that you can use the chain rule in reverse. Okay? And even knowing that, it is still not easy to sort of do it in one line or two lines, just directly using the chain rule in reverse. So, in order to facilitate the use of chain rule in reverse, we have to come up with some notational. We are going to use some notational tools, which is going to allow us to compute antiderivatives by using the chain rule in reverse in more easier. So here's what I mean. Let's look at the more general form of the chain rule. So the general form of the chain rule, which is, first of all, I'm going to let capital F to be an antiderivative of lowercase f. Capital F is the antiderivative of the lowercase f. And let me ask you the following question. If I take the derivative, derivative with respect to x of capital F of g of x, so g is another function, and then multiplied by g prime of x. If I ask you, not g prime of x, sorry. If I ask you what's the derivative of this composition, what would you say? The derivative of this composition is? Well, you take the derivative of the outside, right? Actually, I'm going to write it outside, sorry. Let me write it here. If I take the derivative here, by chain rule I know that I should be getting f prime of g of x times g prime of x, right? You agree with that? Everybody is okay with that. And so, what is capital F prime? That's the same as lowercase f, because we took capital F to be the antiderivative of lowercase f. So what we have here then is f of g of x times g prime of x. That's the derivative of f of g of x. Is everybody okay? Now, the two sides are the same function, so I can integrate both of them and they will be the same, right? So what's the integral of the left-hand side? The left-hand side, the integral is f of g of x times g prime of x dx. So notice that the left-hand side is the composition of two functions multiplied by the derivative of the inside. Okay? And then, if I take the integral of the right-hand side here, let me write it down. If I take the integral of the derivative of capital F of g of x, what should I end up with? What should I end up with? What is that integral? Can you tell me what that integral is? What's the integral on the right side? What is this integral here? What's the integral of d dx of f of g of x? F of g of x, right? Because the integrand is the derivative of that, right? So you're taking the antiderivative of the derivative of that function, right? So you realize that this is just f of g of x, right? It's like asking you to find the integral of f prime, right? What's the integral of f prime? It's f, right? So it is asking you what's the integral of the derivative. What's the integral of the derivative of f of g of x, right? Well, the antiderivative would be exactly f of g of x, right? Because the integrand is the derivative of f of g of x. Is everybody okay with that? Okay, so what I'm going to do is capital F of g of x, I am going to write this in the following way. Notice that I can think of that as f of u, and then I am taking u to be g of x, right? You agree with that? If I write f of u and then I'm basically evaluating the function f of u at g of x, right? In order to get f of g of x. Now, notice that what is f of u? Remember, capital F is the antiderivative of what? Capital F was the antiderivative of the lowercase f, right? So we are taking the antiderivative of the lowercase f and evaluating whatever we get at g of x, right? Do you agree with that? Everybody is okay with that. So notice what's happening here. I started with the integral of f of g of x times g primes of x dx, and I am ending up with the integral of lowercase f of u du, and then whatever that integral is, I evaluate that integral at g, by replacing u. I replace u by g of x after I found the integral of f of u. Wouldn't you agree that the second integral would be simpler than the first one? The second integral would be simpler. Well, let's say usually it would be simpler than the first one. So what are we doing to go from... So what am I doing to go from here to here? What is it that I'm doing? Well, if you think about it, what we really did is the following. Okay, let me write that down again. So I have started with f of g of x multiplied with g prime of x dx, and I have obtained that this is the same as the integral of f of u du, and then whatever that is, I replace u by g of x once I know the antiderivative of that f. This is what we are doing to go from the left side to the right side, but notice what we are doing is that we are taking u. How am I converting the first integral into the second one? I am taking u to be g of x, right? And I am taking g prime of x dx to be du in order to write down the second integral, right? That's pretty much what I did. So basically remember, what is that u and du? Well, that's pretty much what our notational tool differentials, right? So if I pick u to be g of x, then du is g prime of x dx, right? And then if I make these substitutions, I get the second integral. The reason it's called substitution rule is because I am substituting u equals to g of x, right? and I get the second integral, and hopefully the second integral is simpler to evaluate, and then I can evaluate the first integral. Well, let's look at an example to explain what's going on. Let's say I have the integral here, which is the integral of x cubed plus 1, root of that, multiplied by 3x squared dx. You have to find the integral of this. Again, a substitution works because the integrand is the composition of two functions multiplied by the derivative of the inside. So if I look at this integrand, there are two factors, right? 3x squared and the root of x cubed plus 1. The root of x cubed plus 1, that's the composition of what? The root of x cubed plus 1, that's the composition of root x and x cubed plus 1, right? And what's the derivative of the inside x cubed plus 1? 3x squared. So notice that the integrand has that form that I told you. It is the composition of two functions multiplied by the derivative of the inside. And now, if that's the case, then I can use the chain rule in reverse. I can use the substitution rule. However, you don't really have to think about all that. Sometimes in this type of problems, don't overthink about what you to pick. Let your hand do the job instead of your head sometimes. That is, you look at this integral, instead of thinking about composition and all that, just think about, I want to simplify this integrand. And you look at this integral, which term you want most, which one do you hope was x? If you look at this x cubed plus 1 here, you hope that it is x, because if it is x, then you have just root x, and then it's a simple integral, right? Am I making sense? So let that to be your guide to pick your u. So we are going to pick a u, which is x cubed plus 1. And then what is the differential of u? The differential of u would be then 3x squared dx, right? Everybody's okay? Now I'm going to make the substitutions here. I'm going to make the substitution here. This would be, that integral would be equal to, first of all, let me rewrite the integrand as x cubed plus 1 times 3x squared dx. And now I'm going to make it, I didn't change anything yet. I'm going to make the substitution. So I'm going to replace x cubed plus 1 by u. And then this guy becomes what? du. And luckily I ended up with a very simpler integral, right? I know how to deal with a power of u, right? So this is the integral of u to the half du, and then by the power rule, this is 1 over half plus 1 u to the half plus 1 plus a c, which would be 2/3 u to the 3/2 plus a c. And finally, what do I have to do? I have to replace u back by x cubed plus 1. So this would be 2/3 x cubed plus 1 to the 3/2 plus a c. So that is my integral. Wouldn't you agree that if you try to use the chain rule in reverse directly without using differentials, I don't think most people can do it, okay? And so this tool of differentials, it's actually it's making it easy for us to use the chain rule in reverse, okay? Everybody's okay? Yeah. Yeah. Right there.